As My Taxi, which is a popular taxi booking app in Malaysia. In this talk, he will share how to use ZMQ with Node.js to create a service-oriented architecture and learn how to build custom network topologies instead of being constrained to follow a standard one that does not fit your infrastructure goals. So let's welcome him right now. Thank you.
Right, good afternoon, people. So, it's after lunch, and you guys have eaten your lunch. Feel sleepy a bit, so I'll try to make it interesting for you, alright? So today, my talk involves ZMQ. As I know, yesterday, there's another talk about ZMQ as well. It's done by Caesar Chu, right, I think. So, how many of you here have been to the previous talk about ZMQ? Can I see a raise of hands? Awesome, good. All right, how many of you here are back-end engineers, server-side engineers? 1, 2, 3. Well, a lot of you. Okay, so I can't bullshit anymore. So. All right. So the reason for my talk today is to introduce to you ZMQ. I'll explain what is ZMQ first. The reason why I'm doing this talk is because, well, I'll skip the about me part. Because of this. So a lot of times when we are programming in the back end, right, we tend to run into a situation where we are asked to give a solution to something. But if your knowledge only covers so much, then the solution that you create will be limited as well. So there's a saying that if you only have a hammer, everything else starts to look like a nail. So today, I'm going to introduce to you this wonderful tool called Chainsaw. Alright, so let's start. What is ZMQ? ZMQ composed of two parts, 0 and MQ. 0 part means nothing. You don't have anything, alright? MQ means message queue. So when you combine this together, it becomes you don't need a message queue. That's basically the core philosophy of ZMQ. Obviously, the name doesn't reflect the purpose of the library because the purpose of ZMQ is to provide you the tools to build your own network topologies. The reason I say this is to make it simple for you. If you have two servers that need to talk to each other, how would you do it? The easiest way is to create a TCP connection to each other, right? You can send messages to each other. And if you want something more, you can actually add in HTTP on top of it, which is where the REST API comes in. If you don't want to use that, you want something more, something safer, you can always use a message queue. RabbitMQ, AMQP, Amazon Simple Queuing, Super Queue services, and things like that. So what I'm proposing today is a way for you to do the same thing without having to involve installing 100,000 of libraries or subscribing to services that cost you $1,000 a month. So let's begin. Why is ZMQ called as ZMQ when it's not a message queue? It's kind of complicated in a way, but actually the answer is very simple because it has the idea of a smart endpoint, but a dumb network. So what it does is it gives you a super socket. In fact, it's a smart socket, a socket that has a lot of things built into it. So using this socket, you can connect different components in your network, and you can have them work the way that you want to without relying on the message queue. But this doesn't mean that you don't need a message queue, which I'll explain in a moment. Right? So, whenever we talk about message queue, we always have two ways of categorizing them. Do we have a broker, or do we not have a broker for a message queue? RabbitMQ is a message queue that has a broker. In fact, most message queues, when you say a message queue, you indirectly need a broker message queue. Think about it, where this pops up. You can use that as somewhat as a message queue, but still, it has a broker. It has a central service, a centralized service where you send messages to, and you have a centralized service where you pull messages from. So, ZMQ is a networking library, and you can do the same thing. You can create a brokered message queue with ZMQ. You can create a brokerless message queue with ZMQ as well. So that's what we meant. Sorry, that's what I meant when I say it's a networking library. So a very quick crash course to this. Don't worry if you don't understand any of this, because we'll go through them in detail in a moment. All right. So the basic idea of sockets is that you have a buffer. Every socket has a buffer. This buffer is what we call a message queue inside ZMQ. I know it's a bit cheaty, but this is basically how it works. Messages that get sent get stored in the buffer first. If your connection gets disconnected, your buffer contains your message, so you don't actually lose messages to a certain extent. Okay. So the second thing about this sockets is that it has an incoming and outgoing strategy, which I'll explain in a moment. Right. So the next few things is that there are different socket patterns that ZMQ provides. In this particular talk, I'm going to cover push, pull, pop, sub, and only these 4 sockets, and I'll show you how you can use these 4 sockets to create a web server. So the rest, you have a request reply, xpop, xsub, router, dealer, stream, pair, and devices, which we will not cover because that will require several more talks. So let's start. ZMQ is a library, as I've mentioned, right? It supports TCP, it supports IPC, it supports PGM, ePGM, or you can even use it inside the process, which is called improp. So this is where the flexibility of ZMQ comes from. You can either use it to connect to TCP servers. You can, with just a simple configuration change, you can change it to use PGM or IPC as you wish. So every socket maintains its own internal queue. And they have a mute strategy. Okay, I'll go straight to the mute strategy, right? So what is a mute strategy? A mute strategy is when a socket has connected, but it can't send messages. So depending on what your socket is, depending on whether it's a push socket, or a pop socket, or a sub socket, or a pull socket, there are different mute strategies. So think about it this way. I'm going to show you a really professional illustration. Okay, so this is a good illustration of how ZMQ works. You have a producer on one side, which is one component of your network, and you have a consumer on the other side. The producer sends something to the subscriber, right? And this part itself is the message queue, or you can call it a buffer. And this part is when when this connection dies, right? And there are few messages coming into the producer. So what happens? What happens is you go into this queue, to this buffer, until the point where it reaches the high water mark. Yeah, it's kind of hard to write with the mouse, but okay, it will go to the point where it reaches a high water mark. The high water mark is something that says that, okay, the queue is full. You shall not pass anymore. So this is where the mute strategy comes in. What happens to the socket when you reach the high water mark? So there are 2 ways that, do you guys mind if I just use this because it's easier? Okay. So there are 2 ways to do it. You either block the messages or you drop the messages, right? So blocking is very simple. It basically says that, hey, the message is queue. The message queue is full. Do not send any more messages, and you start blocking the messages. They won't come in anymore. Okay. So drop means, unfortunately, your messages goes into the black hole. You send messages in, nobody receives it, and just disappears. Now, this might set off a lot of alarm bells for guys over here that use message queues, because the entire reason of using a message queue is to not lose any messages. So, but like I say, ZMQ is a library. It provides you the flexibility, and it also assumes that you understand the trade-offs. Right? So let's move on. I'm going to show you a request and reply socket and how it works. You can find the code itself inside this repository. inside this repository itself. You can go there, fork it, and you can see tests. You follow the instructions to run the favorite instance to run your test, right? So I'm going to show you a request and reply. How does it work? So, what it does is that, can you guys see the code? I think it's kind of hard to see the code from here, but I'll share the slides later, and you should be able to find the source code inside the repository I just shared just now. But this is all the code I have to write a request and response socket pairing. So what it does is basically this. There's a producer that sends to the consumer. Alright? This is a request, this is a reply. Alright? So what it does inside the consumer is to do something that is really expensive. In my example, it does an allocation and deallocation of memory of binary trees. So it takes quite a while before the consumer returns to the producer the results. Okay, so let's try it out. So as you can see here, it's connected, it's sent, and it's received. And now the consumer side is making a process, it's processing the information. And it takes a while before it comes back. There you see. Okay, so this part is where the consumer sends back the information, sends back the results. And you can see the moment it sends back the results, the producer sends the next request. Okay? So what does this mean? This means that request and reply is a synchronous message pattern. Basically, you have to send out and you wait for a reply before it sends the next one in. Correct? So this goes against everything we know in Node.js. So this is one of the important things that you have to understand about ZMQ. It's written in C++. It's not written in Node.js. Alright? So moving on. Let's look at this push socket, which we'll be using quite a lot in this talk. Alright? A push socket is basically a pipelining tool. It's basically when you say that you're a postman, you have this piece of parcel, you need to pass it to somebody else. So you, as a postman, you're a push socket. You give things out, you don't expect them in return. Sounds like a relationship? Alright. Anyways, so on the push socket, the incoming strategy, there is no incoming strategy because it doesn't receive messages. You use a push socket to push up messages. Hence, the outgoing strategy. The outgoing strategy for push socket is a round robin thing. So what this means is that, let's say you have 3 consumers, A, B, and C, right, consuming your messages. So the first message you send will actually go to A. Second message you send, go to B, and then you go to C, back to A again, and then B, and then C. Alright? So this is what we call a round robin. For those who have used a proxy, or those who have used Nginx as a reverse proxy, you will understand this, what round robin does. Right? For those who are using node clusters, anybody here using node clusters? No. Okay. So node clusters in the next version of Node, it does round robin as well. So this is basically how it works. For the mute strategy, a push socket blocks whenever it becomes full. Let's say that at one point A, B, and C dies. The push has nobody to talk to. It becomes very lonely. So whenever new messages comes in, you will have to put it into its queue. And when the message queue becomes full, it will start to block messages. It will say, don't send any more messages, I can't take it anymore, nobody's talking to me. Right? So this is what the push socket does. So let's see an exhibit of how this actually works. Right. You can see here. Okay. This might not make sense to you right now, but I'm going to analyze with you in a moment. Okay. So this few lines over here is basically the push socket sending out information. It sends out messages to various connected workers. There are 3 workers connected to this particular producer. The first worker, which is yellow, receives the message of 1135, which is this message. The second worker receives this message 1454, which is green. And the third receives the purple receives the message which is purple, right? So as you can see, the producer will push as many messages as possible that it can to the workers, and it doesn't really care about the reply. It just knows to keep on pushing until it's done with all these messages. And then here you see the the receivers. They finally receive the messages, and if you look at the distribution of the colors, they're actually pretty well distributed. You have yellow, green, purple, yellow, green, things like that, right? You can see the code inside the repository to see how it works underneath, but this is a good representation of the round-robin dispatching method that it's using right now. So next, we move on to the pull socket. Using the same analogy as the postman we had just now, a pull socket is you, the person who's receiving the parcel, right? So one day you can receive multiple messages from multiple postmen. So the postman will come, and there will be 5 postmen coming to your house, and you can receive them all. So this is where the incoming strategy comes in. For the pull sockets, the incoming strategy is a fair queue. Fair queuing works by the pull socket taking a message one by one. So if you have 3 producers, you have 3 postmen coming in, you take from A, then you take from B, then you take from C, then you go back to taking from A, B, C, right? So this is to ensure that no producers can overwhelm the consumer. So if one producer produces 1,000 messages, right, you will still be able to grab it when B and C comes back with a message. And I'll show you what I mean. Alright, so as you can see here, there are 3 different producers, 3 different colors, right? We have green, we have purple, and we have yellow. And when all 3 tries to send messages together at the same time, you will see that it's receiving in a fair manner. Everybody gets to send out their messages, right? Now let's make a slight modification to the code to change that. Alright. So instead of having everybody send together at the same time, you're going to have one person send more. And see if it drowns out everybody else. Alright, there you go. Look at this. These 3 lines are what we had just now, right? Green now sends faster than everybody else. Green sends 1, then you have a purple, and then you have yellow. And then green sends again, because the timeout has been reduced. And here it sends again, because before the purple and yellow are able to send out, green has already sent twice. But, look at here. Purple and yellow still gets to send out their messages, even though green is faster than anybody else. So this is how fair queuing works. It basically makes sure that everybody has a chance to send messages, even though they send everything at the same time. Alright? Let's move on to pop. A pop is basically, if you've used PopSub before, a pop is basically that. It publishes things, right? So there's no incoming strategy because it doesn't receive anything. But the outgoing strategy is called fan out. The fan out is basically a broadcast. Right now I'm the pop socket because I'm talking to all of you here, well, most of you here, except those that are sleeping. Alright, so I'm talking to you and I'm broadcasting to you. So if every one of you here are individual sockets, then I am sending to all of you fan out. So this is what we call fan out, and I'm going to show you what it means, right? So alright, so this is a very simple example of fan out. This tree are 3 consumers, sub 1, sub 2, and sub 3. And the color changes on every broadcast. So as you can see, on every broadcast, all the subscribers get the messages. See this? Alright. So, one thing to understand about the pop socket, which is extremely important if you decide to use ZMQ, is that it drops messages. Alright. The default strategy for a pop during a read state is to drop messages. What this means is that if there are no subscribers to a pop socket, if you guys are not here, and I speak something important like a nuclear explosion just exploded in the middle of Taiwan, which I never. Sorry, no, that's well, maybe if you guys are not in this hall and I explain how cute my cat is, and everybody comes into this room, nobody realizes that I even have a cat in the first place because the message is dropped. So there won't be any messages, won't be anybody to receive it. So this is how a pop socket works. So when you use ZMQ, make sure you understand this part. Okay? So I'm going to show you what happens when a subscriber leaves. This is the nice thing about pop socket, or in general all sockets, is that when the subscriber leaves, it still continues to send out messages, but you automatically tackle the situation when the subscriber is no longer available. And when the subscriber rejoins, you automatically add it back to the queue. And this is how it should. This is how it works. Okay, so subscriber 3 says goodbye and it's left, right? And now he rejoins, and you can see here that after subscriber 3 is left, it only sends to sub 1 and 2, right? But when it rejoins, then it starts receiving the messages again. Okay, so this, when you start using ZMQ extensively, you have to understand the downfalls of this kind of pattern, because when a subscriber leaves and comes back, it does not receive the old messages here. It does not. It will only receive the next message that is available to him, right? So this is something that you have to bear in mind with. So next, finally, a sub, which is you guys. Subs. You're all subscriber sockets, okay? So a subscriber socket is kind of similar to what a pull socket is. When you have multiple producers, you use a fair queuing fair queuing incoming strategy. So I won't quiz you guys on what fair queuing is, but the general idea is that if you're listening to me and you're listening to the other speaker over there at the same time, what you do is you listen to me for 1 minute, let's say one message, and then you switch over to the other guy and listen to one message, and then keep on switching. So this is basically how a fair queuing works for a sub. So I'm going to just show you here. Alright. In this situation, we have three pop producers. One is green, one is yellow, and one is purple. So as you can see, again, because of the fact that we're using a fair queue mechanism, everybody gets to talk here and here, despite the fact that green is sending a lot of messages as fast as it can. So that's the idea of a fair queue. Alright, so now that we know the four basic sockets, push, pull, pop, and sub, let's try to build something with them. What we're going to do is we're going to build a simple HTTP server, not just a normal server, a server that you can add and remove multiple workers as you wish. A server where you can start the worker and then stop the server and it will still work. Right? For those who have done TCP programming or those that have played around with BSD sockets before, you should be familiar with this kind of API. So here's the general architecture. So R is where the request comes in. We use Express to handle the requests. And then whenever, on every single request, you send it to the push socket, which you send it to the worker process. Right? So a push socket is always paired to a pull socket. So after that, the worker process will pass on the message to a handler, which is basically your model in your basic MVC framework, right? And then once it is done, you use a pop socket to publish it back to the server as using a sockets, right? So I'll show you right here what this means. Is that clean all this? Okay, I'm going to run the server here. And as you can see, it's listening to port 13370, and it is there's a pop socket and a push socket that's been initialized in here. So I kind of forgot about this. Okay, so as I start the worker, as you can see, the server detects the worker connecting. Right? I'm going to start another worker. So now, we have two workers connected, 1 and 2. If I remove one of the workers, then the server stays up. If I remove both workers, then there basically is nothing the server can do. So if I try to do a clone right now, there, it will fail. But the server will not die, because I'll just face the fact that it doesn't have any workers. So now let's start by both workers. Let's do that again. And here, you get the results comments. So this might not seem to be a very interesting example, but the fact is, I hope you can see the potential in this thing, right? Think about it. You have a server that can stay up, and you have a bunch of workers that can connect to it anytime it likes. No configuration changes, right? Anytime you want to connect, you connect, and you start receiving jobs, and you can reply to the jobs. So what this means is that all your business logic you can put them into your worker. And I'm sure all of you here have the experience of configuration changes, right? When you change the configuration, you've got to restart your server or something. So instead of restarting the entire server, you just restart the workers one by one. Your connections inside the server will not be affected, right? But you can start all your workers, and your workers will get a new configuration, and when they connect back to the server, you'll be using the latest configuration. So this allows you to create a topology where you won't lose connections, which is important in some use cases, right? Now I'm going to show you what happens when the server goes down rather than the workers go down, right? I'm going to kill the server right now. See, I did not write this reconnection code. This is what ZMQ provides. The workers will automatically try to reconnect to the server, and when it comes back up, you automatically connect back to the server as if nothing bad has happened. Right? So, the conclusion that I want to draw and I want to bring your attention to is that ZMQ can be considered an extremely lightweight networking library. And the good thing about ZMQ is that it is written in C++, not because of speed, but because this means that Node.js is only one of the language bindings. If you want to write a worker, say in Python, or you need to write a worker in Ruby, you can do so. You can use the same server, you can use the same sockets, but you just add a worker that runs on Python to your server. So what this means is that if you have certain programs that you can't do in JavaScript, like if you want to do stream processing, video processing and stuff like that, and you want to use a raw C library to do that, you can actually connect them to using ZMQ. One of the benefits that you can have by using this kind of library. So the more important thing that ZMQ provides to you is the second point. To build messaging topologies that you want. This is important because if you have used RabbitMQ, it's an excellent product. RabbitMQ is super nice. But the problem is, it tends to tell you how you should structure your topology. What if your topology doesn't fit RabbitMQ? So this is the part where you have to make a decision on whether you have to build your own messaging queue, or you can use something like ZMQ to give you the connectivity that you want while you search for a better solution, or while you improve your current implementation to a level where it's production ready. right? So the rest, I've kind of demonstrated it. We have asynchronous features where you add keyword workers as you wish. You can connect applications written in different languages or different technical tech stacks. And it's basically a good tool for you to use and understand. So once you know about ZMQ, there really is very little reason for you to start using things like doing raw TCP programming and stuff like that, because you do have a tool that does most of the job for you, unless you have something that's really, really specific that ZMQ does not cover. So further references on similar projects or offshoots, you can look at NanoMessage. NanoMessage is a fork written by Martin Sustrick, which is the one of the founders of ZMQ. It's ZMQ rewritten in C, pure C, and it covers some of the drawbacks of ZMQ that NanoMessage addresses. Next you have Axon. Axon is done by Vision Media. You guys should know who Vision Media is if you are using Node.js. They came up with Axon, which is a pure Node.js implementation of ZMQ. And then we have articles about the theory of ZMQ, its internal architecture, as well as an article dissecting different kinds of message queues, including things like Kafka, things like RabbitMQ, and ZMQ as well. So, which brings us to the end of my presentation. I hope I'm on time. So, I hope that this talk has given you open up your mind to some possibilities that you can have while deciding on how to structure your network infrastructure and how to even build multi-threaded programs. You can actually use ZMQ as a way to pass messages between threads inside a multi-threaded program. And if you want something you can even connect raw TCP connections to your topology, to your ZMQ infrastructure by certain socket patterns. So, I hope this helps you. Do any of you here have any questions for me? Yes.
Is there a bandwidth problem, or if there's too many requests to the server or to the service, to the worker?
Okay, your question is would there be any problem if there's too many requests, right? Okay, this is, when we talk about this problem, we are addressing a scalability problem. There are many ways you can use to address this, but on the most basic level, like I say, the sockets provide a high watermark. So I'm going to use this amazing tool. I love this tool. So when you have a lot of messages, right, coming into the socket, and you can only talk to so many people at the same time, right? So what it does is to start filling up this queue, this internal buffer here. You fill up here, and these things will go out, try to set it up to the consumers as fast as you can. But in the possible situation where this internal buffer has been full, depending on which socket you are using, then it comes to the idea of a mute situation. Alright? So if you're using a push socket, it will block the messages coming in. Messages tries to come in, bam, block. Right? So this is something that you have to handle in your code itself. This is only the basic safeguard that ZMQ provides to you. Alternatively, you can increase the high watermark. So here, you have 5. 1, 2, 3, 4, 5, right? You can only hold 5 messages in this queue. What you can do is to raise this ceiling, so let's say another 2. So you're raising the high watermark to ensure that you don't block too many messages. So by the end, to answer your question, like I say, it's a scalability issue. And if you are relying just on ZMQ to do it, be prepared and expect to do some work on it, because ZMQ does not do that for you. It has basic safeguards against it, but in order to survive production environment level of traffic, you have to do some work to it. That is where you start using things like saving your messages somewhere and adding your own quality of service, QoS mechanisms to ensure that you don't lose messages.
Thank you.
Any other questions regarding this? Yes.
Do you have any project using ZMQ?
Yes, I'm working in My Taxi, which is a taxi app in Malaysia, and there's one service that we are using currently, which uses ZMQ, uses push code. And one of the reasons where I choose to use this thing was because of the flexibility it grants me. So here I'm going to draw some very nice illustrations for you. Okay. So this is my server, and all the incoming messages comes in. I have a bunch of workers like this, and I designed it in a way that you can actually take these workers and put them into individual server boxes, just in case the workers start to consume too much resources and all that. They all communicate through TCP connections, right? So to answer your question, yes, we are using that in production right now. It has worked out really well for us. It does load balancing properly on top of the load balancers that we already have. And so far, I'm happy with it, and I think it's a much more superior solution compared to node clusters as of version 10. So, yep. Does that answer your question? Good. Alright, anybody else with questions? Alright. I was just about to start juggling cats. Yes.
I have heard from Malaysia, right? I'm Malaysian too.
Yes.
And I want to know what is the trend of programming nowadays in Malaysia?
What is the trend of programming?
Yeah, no, it's not about ZMQ. I'm just curious. I want to know what is the trend, the trend of programmers.
The trends of programmers, the language that they tend to use, right?
Yeah.
Okay. The thing about Malaysia is that it's not like you guys here. We don't have this kind of big conferences for JavaScript. In fact, from what I understand, I feel that PHP is still quite strong in Malaysia. So PHP, Ruby is kind of hard to find people to hire. JavaScript is still very young. Not a lot of companies are using Node.js as their backend tools for good reasons. There are still a lot of Java people, a lot of .NET people, and a lot of PHP people. So it's kind of like an old town kind of thing. So I'm not sure if that answers your question or not, but I hope it does. So any other questions? You can ask in Chinese if you want to, because I understand Chinese as well. So if you're not really familiar with English. Anybody else? Sorry about that. Yes.
可以秀一下你的current 的那个 example， 就是你们公司现在在用的 example， 就是 push。
Okay. So the question is, can I show the example that we're using currently for our system? It's basically a point of interest service. So what is a point of interest service? It's basically a service where you query it and you get a response to a bunch of locations near that area. I would love to show it. I can't because it is an internal service, mainly because it's an internal service. But the example that I showed here, this web server, is almost exactly the same as how the POI service is written. So if you, the code is there in the repository. I'm going to show you the repository again. It's inside here. So if you want to find out more about how the server itself is written without all the business code, this is basically where you go to. Get into this repository, go into test/talk, and the code is all the code is inside there. So that's a reference point for you. So anybody else? Yes.
喂，不好意思，我用中文发问，就是刚刚的 demo 是 one server to multiple worker， 那有没有可能用同样 ZMQ 的机制去做成 distributed 的环境？那就是 multiple server， 然后无论是说是用 master slave 的机制，或者是 ZMQ overlay 机制，让多个 server 同时 serve request。
Okay. So the question in English, I hope I get this right, is that it's asking whether it's possible for us to create a cluster-like environment where you have multiple servers talking to multiple workers. Is that right? Okay. Yes, it's definitely possible. I'm going to show you a slide here. So let's say a push-pull, right? This is a push, how it works. It's one server, one push server talking to multiple consumers. The consumers, on the other hand, is a pull socket. So as you can see, if you look at these two graphs, these two illustrations, you will see that it's entirely possible to connect multiple servers to multiple workers with very minimal overhead code. Having said that, of course, it involves quite a lot of extra work if you want to do something that resembles a multi-master environment, multi-master cluster. Because when you do something like that, you're basically threading into distributed programming territory. You run into problems where you have to determine consensus between multiple masters. You have to understand what kind of trade-offs are you going to use. Are you familiar? Sorry, you're familiar with the CAP theorem? So when you have multiple masters, then you have to start to think about what kind of things you have to sacrifice. Do you want to sacrifice consistency, or do you want to sacrifice availability? So it's kind of a tricky situation there. But to answer your question, yes, it can be done. In addition to that, expect to write a lot more code to make it reliable. So I hope that answers your question. Right? Anybody else? Yes.
How many people are there in the team working on this project, and how do you guys distribute the work?
Okay. The question is how many people we have in our team and how do we distribute the work. Initially, it's just me, the only person advocating the use of ZMQ, because it's not a simple thing to understand. But as the project has passed through the hands of 3 different persons, we used to have 3 persons working on this project, and now that it's stable, I'm the primary person maintaining it, and every now and then there are other Node guys that works on it as well. So to answer your question, there are several, our team consists of probably about 20 plus people, but they're not all on the backend team. There are some mobile developers, we have graphic designers, 2 or 3 graphic designers, we have the web application side people, and then we have the backend people like us, and then we have DevOps people like us as well. So, yeah, hope that answers your question.
You mentioned before that JavaScript people are really fine in Malaysia.
Yes.
So your company, your team is quite unique there, and also why? What was the reason that people don't choose to use Node.js in Malaysia?
Oh, that's a very good question. Okay, the question is that when I mentioned that JavaScript engineers are hard to come by, actually good JavaScript engineers are hard to come by, but why are we using Node.js as a tool, right? So here's the thing, the person that wrote when the company started up, the person that was in the startup happens to know and love Node a lot. So when you have only a hammer, everything else starts to look like a nail. That's why we chose to start with Node.js. But the good thing about it is that it's not a bad decision per se. It is a decision without, well, not to say without, but it's not a very, it's not a decision that you can back up with a lot of technical decisions behind it, but still, it gets the job done. And it still does get the job done nowadays. Node.js is a very powerful tool, and we made the right choice, by accident or by knowledge, I know, but still, we made the right choice, and we're happy with it right now. As far as hiring JavaScript engineers goes, you'd be surprised how many people that uses JavaScript has no idea what a closure is. That's actually one of our interview questions. Do you know what a closure is? If you don't, here's a no. So, but still, we do have several Java engineers that we found. We pay them a lot of money. We throw whole bars at them to make them stay, and we make sure that they're well fed. There's lots of beer around, and you get to work with stuff that they're really enthusiastic about. So that's how we try to keep our people with us, and how we hire people at the same time. So thank you. Hope that answers the question.
Thank you.
Okay, so still have time. I'm still available for questions. I'm a very friendly person. So I'm just curious, how many of you here? Oh, sorry, yeah. Yes.
Sorry. Do you ever compare the type DB or Java SQ between ZMQ?
Sorry, could you repeat that question, please?
I mean, there are so many SQ systems like TimeDB, like Java, ZMQ. So, why you choose ZMQ in your system?
Okay. I think the question is, while there are many other messaging solutions and message queue solutions out there, why did I choose ZMQ? Is that correct? Okay. First of all, you have to understand that ZMQ has a very powerful backstory. It came from an initiative to create a messaging library to facilitate stock transfers from a financial situation. Later, in the next year, they start to generalize the message, the library itself, and then they did a lot of research into how to ensure performance is met, and how to ensure to create a library that fits the general use case of most people. So I think ZMQ has a very strong technical base, which is one of its advantages moving forward. But to answer your question, no, we don't just use ZMQ only in our company. We do use RabbitMQ as well for a while. We even use MQTT as part of our connection on the transport side, right? So we also use Redis simple queue made using Redis for certain consensus problems between the servers. So to answer your question, ZMQ is quite a solid product for one. Number two is that our use case for ZMQ does not require something as heavy as a RabbitMQ or anything that resembles AMQP. So that's why we chose something really lightweight, gets the job done, provides just enough safety mechanism for us to handle what we need to handle. So does that answer your question? All right, thank you.
Does anyone still have a question? Okay, there. Okay, last question, please.
An easy one. Will you share your keynote?
Oh yes, I will. I'm going to upload this as SlideShare. I'm not sure if there's a best place to share it. It's going to be on SlideShare, and it's going to be in the repo itself. It's written, it's using Keynote, so I hope you guys, I see a lot of Apple signs here, so I assume that most of you'll be able to open it. And I'm going to share the PDF version of it as well. So
Let's thanks for Ruben sharing about ZMQ. Thank you.